We will be starting in few minutes. Today is the last lecture. Uh, okay, we will start off with GAN, which I had previously covered in the special session as well. Uh, so, uh, so I have explained this previously, like discriminative and generative models. Okay, and so here we need to find new data set. Okay, generate new data set. So it is a zero sum game between the generator and the discriminator. Okay, and they converge at the Nash equilibrium. And so as you can see, this is model 1, model 2. They are in a game, they are fighting each other. Okay, and some examples. Okay, so uh, the work of the discriminator is to decide here which the image that is generated or image, if that is real. Okay, let me explain better. Okay, so what happens here is this. So this is our generator and this is our discriminator. uh, so discriminating is receiving one image. Okay, so it has to decide whether that image is generated by the generator or it is coming from the source data set. Okay, so that is the basic concept here. Okay, and if the discriminator is able to recognize that accurately, or means it gives a higher probability that it is a generated one. So if it is a generated one, then uh, the generator is retrained to uh, fool the discriminator next time. Okay, so the process continues until we have reached an equilibrium, uh, and then we stop the process. Okay, now the generator is trained, and it can produce new images. Okay, so that is a basic concept. Technicalities I have went in the previous lectures. Uh, so if that is not required, then I will not go there again. So these are two deep networks, generators and the discriminator. Okay, so the discriminator gets either the generated image or a real world image, and it has to decide whether it is a generated one or a real world one. Okay, and this is the cost function. Okay, that we have here. Okay, and so I've explained this part as well. First minimize then maximize. Okay, minimize over t. Okay, it has to be reduced and maximized over g, cost with respect to g. Okay, I mean to say, as you can see here, this gz is there and tx is there. Okay, so we're maximizing with respect to gz, but minimizing with respect to dx here. Okay, so summary is here important. Okay, for this course, not so much details is important here. Okay, so so as you can see, real world images. So you take one sample, put it into discriminator. Okay, or generate this generate images from uh, latent random variable is the noise. Okay, so it transforms the noise into a sample and then feeds into the discriminator. Okay, the discriminator decides whether it is a real or a fake one. Okay, so d over x, okay, or d over g of z. Okay, that is the function we get. So z is the random noise, Gaussian or uniform, can be thought of as the latent representation of the image. Okay, so we're back propagating the loss to train the generator and discriminator here. Okay, so so you will have convolutional layers in the deep networks of it. Okay, and so this is the discriminator part. Okay, and it has to decide whether, and to have better representation you can use up convolutional layer as well, which is represented by dcon here. Okay, so dcon 1, dcon 2, dcon 3, right? So it leads to better representation. Okay, and cycle GAN is important. Okay, so cycle GAN, what does cycle GAN do is it it trains, means you can what you can do is that using cycle GAN, after training the cycle GAN, you can you can uh, take the generator, one generator. There are two generators in a cycle GAN. Okay, means two GAN networks. Okay, so you can take one generator and use it for domain adaptation. Okay, this what is called domain adaptation. So you're changing from one domain to another. Okay, and so the training process is here. Okay, so so an input image is there and reconstructed image in another domain is there. So when you run the training process, the input image is converted into reconstruction to input. Okay, so if you remove the GAN2, generator 2, you can use GAN1, generator 1, for constructing uh, this image in this domain. Okay, this reconstructed one domain. Okay, that is why how you can do domain adaptation using cycle GAN. Okay, and so uh, so using the the deep networks of the GAN, you can also do segmentation. As any convolutional networks with the up convolutions can be used for segmentation, so it is not very difficult. Okay, as I said, the generator is a unit based network. Okay, so unit based models can be used for segmentation work. Okay, so that is simple here. Okay, so that is the convolutionals and then deconvolutional layers for. Okay, so that is what we have done. Acha, is it audible to everyone? Is it audible?
Yes, sir. Audible.
Okay. So, so segmentation and loss function is defined here. Okay. Uh, okay. Not very important actually. Okay. Okay. So that is the idea of the GAN here. I've explained previously in the previous lecture as well in more detail, technical details, but it is like overview over this one. Okay. Uh, so let's solve some problems here. Okay. That are given here. So what problems in machine learning are can commonly used to address? So they are used for data generation, right? Or you're trying to generate new data using the generator part of the generative adversarial network. Okay, so for data generation. So this mode collapse is like it is producing limited variety of output data. Okay, so this is the answer. So what does it mean actually is that the generator is not producing the variety that may be expected from it, or what we call this in this case is that the generator has an inherent bias to it. Okay, so that is called the mode collapse of generative adversarial network. When it has developed bias towards certain type of generation. So what we can do to resolve this is make the models more robust. Okay, so making the model more robust can avoid this problem. How can we make the model more robust? uh, by introducing data that are diverse. Okay, so that can help it. Okay, and another is like normalization. Okay, normalization also helps. Different normalization schemes are there, batch normalization, etc. Okay, so this can also help in more robust models. Okay, adding means like, and also what you can do is that you can add extra noise to the input data set. Okay, and that can help in creating a more robust model that does not produce mode collapse. Okay, so the primary limitation of GANs is it is computationally expensive. Okay, nothing much here. Okay. Okay, so the next focus goes towards autoencoders. So we'll focus on that. So in the previous session that we had, I covered variational autoencoders. So the autoencoders that we cover here is like the general class of autoencoders. Variation is a special type of autoencoder. Okay, uh, which uses the concept of variational inference. Okay, but this is a general one. Okay, so we go really basic here. As you can see, the CNN model is covered here. So convolutional layers with non-linearity one after another. Okay, then fully connected, then you can use it for classification. Okay, so you can use this for classification okay, and so this pooling layers are called downsampling unit, as well. Okay, so for a reference here. Okay, so next we go to semantic segmentation here. Okay, so we need to segment areas which are and classify them in that image itself. Okay, that is called semantic segmentation. You can see in the examples. Okay, and we need a unit network for semantic segmentation, having a downsampling as well as upsampling. Okay, uh, so segmentation, as you can see, uh, so, so you need to prepare unit network. Okay, and how is it prepared actually? So as you can see, the image size is large here. Okay, so you do down sampling using convolutional layers with pooling. Okay, then you upsample. Okay, upsample with deconvolutional layer. Yeah, you can find deconvolutional layer in any any coding library. Okay, machine learning library, PyTorch or TensorFlow. Okay, and to store the spatial information in the upsampling process, the the downsampled parent, you can say, it is concatenated to the concatenated to this, as you can see, this is concatenated and then upsampled. Okay, so this is important. Okay, it is used for preserving the spatial information. Okay, and so just some calculation here. Okay, so from unit only we get the encoder decoder representation. Okay, after the encoder has finished its works, we get an encoded representation. Okay, okay, so this is the encoded representation, and so it is representing the segmentation operation. Okay, so the contraction phase reduce spatial dimension but increases the what. Okay, so during the contraction phase we are reducing the spatial dimension. Okay, the size of the feature space is reducing. Okay, but increases the information about what is represented by the image. Okay, in the expansion phase we are recovering the information where the object lies in that image. Okay, so that is where. Okay, so as I said, this concatenation helps in recovering the where information. Okay, during the expansion phase. Okay, okay, I think I finished here. Auto input part was not covered, I think. Mm. So what are autoencoders? These are deep networks. Okay, um, these are used for coding the input data. Okay, and the training set is unlabeled. Okay, so this is unsupervised learning. Okay, so these codings have much lower dimensions, so it is used for dimensionality reduction. Okay, so efficient data representation and likewise. Okay, and so this is called autoencoders, auto plus encoders. So encode the input, so dimension reduction, invertible mapping. Okay, uh, so okay, and so it is for use can be used for classification after encoding, or used for feature selection. Okay, and so likewise. Okay, this is how a autoencoder looks like, just a neural network, simple, but the input dimension is lower. So so this is backpropagation for learning the weight. We minimize the mean squared error. Okay, so no labels are required, and so autoencoders have several uses here. Uh, so first is the dimension reduction. Okay, so feature detector is also another. Important features are detected. Okay, others are removed. Okay, unsupervised pre-training of deep neural networks. Okay, so this is a pre-training approach. After that, modern generative models like diffusions can be used. Okay, and also it can be used as generative models, as we have seen variational autoencoders. Okay, so these are the various varieties of autoencoders: sparse, stacked, variational, denoising, and contractive. Okay, so these are the type of autoencoders are there. And so we finished the little introduction of autoencoders here. Okay, so so at what condition the autoencoders perform PCA? Okay, means the selecting the features. Okay, so we're minimizing the mean squared error, and a single linear bottleneck layer has to be there. So we are actually selecting features. Okay, or dimensionality reduction. Okay, and so so the activation function is linear. The loss is mean squared error, and has a single bottleneck layer. Okay, so in that case it can be used to perform PCA, so to reduce the dimension. And so the why the encoder is linear is required. We do not want to transform it into a different feature space. We want to keep it as it is. Okay, so image should remain as an image, or something like that. Okay, uh, do not want to transform it to a binary scene. Okay, so that is why this linear non-linearity is important. Activation function. Okay, So these are all the benefits, okay? Many. So reduce dimensionality, okay? So many instances features can be reduced, handle large data set, okay? So this bottleneck layer is the final layer. It is used for extracting and coding useful features, okay? So only useful features are retained, others are not retained, okay? Now we'll look at a little bit about recurrent neural networks, okay, RNN. So this is the overall structure of the recurrent neural network. So xt is here the input, okay, and what happen is that you get the input, give the input, okay, it gives you h output, but it is then fed back again into the network, okay. So that is how we get ht minus 1, okay. So it is a again fed back 1, okay. It gives ht, second fed back 1 ht, like that, okay. So that is why that is how the RNN is defined. That is the structure of the RNN, okay. So that is how you can see. So h0 and x1 is fed, okay. H0 is some can be random hidden state, okay. So it produces h1. This h1 can be used to produce y1. So h1 is a encoded form, okay. So that it can be decoded to yield y1, okay, like that. It happens in repetitive steps, okay. Okay. So this is how you can see h1, h2, h3. It produces different y1, y2, y3. So this tan hyperbolic is used as the non-linearity to produce another ht here, okay. So very important, the weights are shared over time, okay. So there are many useful applications of RNN. First is sentiment classification, okay. So the input is multiple words, one or more sentences, okay, whatever, okay, and the output is one or zero, positive or negative, like that. Uh, so, so examples you can see here. So, so so you can see the example in this structure. What you are doing, that this this is the x value, okay. So it is being fed, okay, x value. Some h0 is also there. Output h1 is fed into this one. H2 is like that, okay. So h0 is a our construction, okay, can be random, okay, anything random of some dimension, and so you have to ignore the previous hidden ones, but last one has to be classified as yes or no, okay. Then after training this model, you get the answer while testing whether it is a positive sentiment or a negative sentiment. Or a more holistic approach can be taking the a sum function and summing them over to get this one, okay, to learn that, okay. And next is image captioning. So you have given an image, okay, and need to caption, okay. So the input is in the form of image, okay, x value, that is it is passed through different layers, okay. So you take the every hidden layer, okay, and you interpret it in the form of words. Okay, so much more details are required to understand it properly. Okay, so several other applications are also there. Okay, uh, okay, so several other applications are also there. So so single input and multiple output is image capturing. Single input and single output is like feed forward network. Okay, multiple inputs, centimeter classification. Okay, so means like several words are there, but whether it's good or bad, it is 1 centimeter. Okay, multiple input and multiple output is translation. Means uh, you can understand from English to Hindi translation. Okay, so like that. Okay, multiple words here as well, multiple words here as well. Okay, then there can be image captioning. So image can be input in the form of pixels. So there are several pixels, and and several words as well in the output. Okay, so this is the one. Okay, you can have more details on it subsequent lectures. Okay, but we are not going into too much details here. So the primary advantage is this one, because there are common weights for every time steps. Okay, so they can model dependencies across time steps. Okay, uh, so means like the same weight is used at every time steps. Okay, and that weight is updated. So that is a major benefit of RN. Given an input image, what is the output of the unit architecture? So output is what, a segmented mask with the same resolution as the input image. Okay, so we're doing image segmentation. Okay, so we get a segmentation mask having different labels, 0 1 2 3 whatever. Okay, so it will be something like this. So this is the segmented mask we have, and this is one area, this is one area, this is one area. So this is 0, this is 1, this is 2, 3, 4, 5. So these are different areas and different, these are called mask. Okay, so this is the output of the unit architecture. So the contracting path is useful for capturing context information. Okay, and so this skip connection is for, so this is from the ResNet paper. We can cover the ResNet paper here. Okay, so it is for creating shortcut for gradient flow and preserving fine grained detail. Okay, so let me explain this one. Okay, uh, so what happened that there was going on the this ImageNet test competition. Okay, so researchers all around the world were developing their their own deep networks, and to classify the data set, that is the CIFAR 10 data set, as you can see. Okay, CIFAR 10 Okay, CFR10 dataset they were using, and to produce best possible performance. Okay, now what happened is that they started increasing layers after layers, so that the performance could improve. Okay, so because common sense told that increasing the layer, the performance or the accuracy should improve. Okay, so okay, so that is one thing. Okay, now what happened was that after increasing layers, as you can see, so even the training error was increasing with increasing layers, as you can see. Training layers 56 layers is more than 20 layers. So, so they thought that increasing the layers was going to reduce the error, but the contrary happened. Even the training was not done properly. The test was, of course, worse. Okay, okay. So that is what problem they have. Okay, so that is when we needed this skip connection. Okay, so the logic is written here. Okay, uh, so in this problem, in this paper, we address the degradation problem by introducing a deep residual learning framework. Okay, so as you can see, instead of hoping each view stacked layer directly fit their desired underlying mapping, we explicitly let these layers fit a residual mapping. So they were trying to fit a residual mapping to solve the problems. This is the structure, as you can see. So whatever this is transformation, linear transformation is, okay, so this is fx plus x, so x from here. Okay, so the underlying mapping is represented as h of x. So fx here is the mapping of this layer is hx minus x. Okay, we hypothesize that it is easier to optimize the residual mapping than to optimize the original unreferenced mapping. Okay, so it's easier to optimize this reference mapping. Okay, so this is the shortcut networks are there. Okay, and so it's going to be trained with SGD, stochastic gradient descent with a back propagation, and so that can be done. Okay, so they found very good result with this extremely deep residual networks. Okay, in imaginary data set. So they won the first prize in 2015. So due to this residual connection. Okay, this is the residual connection that was used in the unit. Okay, so this is the motivation. Okay, from this resonant paper. So if the time, so some from other is like programming uh, concepts are shared here. If the dimension does not match, you can do a linear transformation using WS, a transformation matrix here. Okay, so that these two can be added. Okay, so this WS can be a transformation matrix for the time, so the dimension match, and you can add using this relation. So this is how they have implemented as well. So So this graph is an important one, as you can see. So the training on the ImageNet data set, okay. So this thin curves, okay, this thin curves, as you can see, denotes training error. Bold curves denote validation error of the center crops. Left. So these are plain networks without residual connection, and these are with residual connection called ResNet. Okay, so this is now the terminology comes. Where do you get the terminology? ResNet means the residual connection having 18 layers, 18 convolution layers. Okay, 34 convolutions layers. Okay, so this is the one. Okay, so you can see the difference actually. First, let's compare it with the 34 layers. Okay, with ResNet, the training error has reduced to I think 25, right? And with plain network, the training error is like 32. Okay, so so it has considerably reduced from 32% training error to 25% training error using a ResNet connection. In case of 18 ones, as you can see, the error is 30% training error, and here it is. Uh, means close. Okay, so means what happens is that, like with increasing layers, the ResNet performs exceedingly better compared to the less number of layers. So these were the importance of the ResNet connection. Next, we can cover more on RNN as well, and so if I can have some slides here. I did not know that RNN was in such sparse details here. I would have desired to cover it in more details. Uh, so maybe we can find a slide here. Okay. So maybe I can explain it from here. Okay. So recurrent neural networks, as you can see. So so the hidden, that was H represented there, it is represented by A here. Okay, so A0 is fed. Okay, and along with the data X1. Okay, so you get Y1 from the first RNN iteration. Okay, and repeatedly like so. Okay, so okay, so A or H is the compressed hidden representation. You can you can regain the final answer YT using this transformation. G are usually tan hyperbolic activation function. Okay, and so what this blocks can be uh, this blocks can be common neural networks, or they can be a specialized called LSTM. Okay, can be LSTM as well. Okay, so this is the structure of the LSTM. You can see, you can find more details on LSTM in some other test. I'm not going to go in depth in LSTM. Okay, and so pros and cons of this 1 minute. Okay, uh, so so advantages, as you can see, the possibility of processing input of any length. Okay, that can be done. Okay, you have just increase the okay. So computationally slow as well, because the as the number of layers keeps increasing, or iterations keep increasing, it becomes slower. If the sentence length is long, it can be a big problem. Okay. The weights are shared across time, as you can understand. So these two equations are very important. Okay, so let's see what is there. uh, this is weight AA, as you can see. So A t minus 1, okay, is multiplied along with it, and so these two weights are there. Okay, BA. So these are Bragg propagated and calculated while training. Okay, these weights, and as you can see, this is we saw earlier as well. Okay, so the Bragg propagation algorithm is written here. Okay, uh, so you have some serious problems with RNN as well. This vanishing and exploding gradient. Okay, one solution is gradient clipping, another solution is using LSTM. Okay, so this is how they have used LSTM. So there can be variants of RNN as well. This bidirectional one, and there can be many layers of LSTM as well. Okay, so these were the examples that were given earlier as well. And to calculate this hidden representation at H1, H0 has to be input, right? So this some hidden, making hidden terminologies are there, like skipgram, negative sampling, glob embeddings. Okay, these are there, you can check these out. Okay, so machine translation is the most useful, or you can say the most exquisite use of recurrent neural networks. Okay, translating to another language, suppose. So you can see it like this. Okay, so at every node you're getting every timestamp you're getting an output. Okay, so this is our answer. Okay, that is how you get a, but it is more complicated than that actually. So it produces probability for different words here. Okay, which words it can be. Okay, and the highest probability if you take it, so that is how you choose it. But there can be like, you take the highest probability over how many samples actually. Okay, so this, that number is called the beam. Okay, and this searching for the best possible value is called the beam search. Okay, so some these and that things. Okay, so attention is another important concept here. Okay, uh, so attention improves the performance of this recurrent neural networks. uh, okay, and so this is the definition of the attention. That is the that is basically the softmax. Okay, of this values. Okay, these are some important concept, but this course is quite limited for that. But maybe we can cover a little more. Attention. So you start with so we start from here to get the attention. concept. Okay, so this is the first paper on attention, and let's see how they have explained the things. Okay, so so RNN, we start off with RNN. Okay, so RNN decoder encoder system is there. Okay, so it was proposed in 2024 by Cho et al. And Skutskiver et al. Okay, and so here they proposed a novel architecture for machine translation apart from RNN. Okay, performing better than RNN. Okay, so so this is the functional form of the RNN. You know it as well. So it takes the previous hidden output and produces new hidden output. Okay, and using C you can produce the final inference. So so they are assigning a attention score to output of the each RNN timestamp. Okay, so, and what they're doing is that using for calculating C, earlier what they did was to just take the HI, but they are summing over having an attention weight. Okay, here, and this attention weight is this one. Okay, this is this. Okay, and what is E here? E is this a function, right? I think so. Yes, it is a MLP, you can say, a small neural network. Okay, to get the values of EIJ. Okay, so this is trained. Okay, and from there you could get EIJ to get the weight, attention weights, A alpha IJ, and this can be used to train the this can be used for inference. Okay, better inference. Okay, so attention score will determine which hidden output is more important. Okay, that is the concept overall. Okay, and after that we get to the concept of transformers, which actually really removes the anything to do with RNN. Okay, so we get to the transformer. Okay, absolutely different concept. Okay, it transforms the means like all the all that we knew about how machine translation can be done. Okay, so this is the transformer architecture. So so overall, as you can see, so the input embeddings 8 zeros we have. Okay, so we add position embeddings encodings to them. Okay, so because the RNN structure will not be maintained here, means like it is not sequential, the information flows at once. Okay, that is why the position encodings is important. You can ask your doubt if you have. Okay, and here we apply the multi-head attention. Okay, it is harder to explain here without any demonstration. I think we should finish off here. Okay, you can read about more about transformers on your own. Okay, so this was the last session, and this is the end of this NPTEL course, and hope you have hope you learned something and move forward with this learnings. Okay, thank you very much. Okay, we are closing of this meeting.